Yes. And we discussed that basically instruction set architectures are of three types. Excuse me. Just a minute. Yes. So based upon their internal storage that they use in the CPU for the storage of intermediate instructions and data, they are classified into three main types. The stack based stores all everything on the top of the stack, and all the operations are also performed on the top of the stack, and the result can be retrieved from the top of the stack, while an accumulator based had one of the operands into the accumulator and the other one could be in a register, and then the results were available also in the accumulator. The third one was a register based architecture. In a register based architecture we had again three choices. We could have had register, we could have had register memory, and memory. So out of these three, we observed that since registers are always faster than memory and they are easier for a compiler to be used, and then they can be used more effectively as well, so we always prefer to use register architectures. And for this DLX processor we are using register based architecture only. All right, then we discussed the five main classes of instructions that are available with the DLX processor. And we moved on to the first class, which is the load store instruction set. So in a load store, we had okay. Anyone who will tell me why do we use load store operations? Why do we use load store operations? Anyone?
To access the memory.
Yes. So by default, this RISC-based processor uses load store operations to access the memory. It can load data from the memory into a register or store data from a register to a memory location. And we have three types of load store possible. We have the load word, load half word, and load byte. Similarly, we have the store word, store half word, and store byte as the three operations. The syntax for all remains the same. So it was a destination in load, it was a destination register followed by a displacement and a base register. So I type of encoding, and this is a base displacement addressing mode. Similarly, store word also has the same format. So you have a source register. It's written RD here. Okay. So it is the only operation. The store is the only operation wherein RS and RD are not written according to their actual convention. I'll explain this when we talk about the hardware of DLX processor. So a store word again followed by a displacement, a register, and another register. So this RD is the value which has to be stored to a memory location. Then we discuss the load floating, load double, and I guess this is where I left. यहाँ छोड़ा था. Yes. So when we talk about the load floating, this was used for loading any data from the memory into a floating point register, 32-bit value. Store floating stores the floating point value available in the register to the memory, and load double was used for 64-bit load. So if we have to load a 64-bit double precision data into a register pair, we use load double. मैंने इसका एग्जांपल दे दिया था शायद लास्ट टाइम. I guess this is where I finished. So today we have to move on, and the next operation that we had to discuss was load half word unsigned and load byte unsigned, right? So again, when I take say I take an example of this instruction. This says load half word unsigned into register R1 from a memory location which is 2, 3, 4, 5 plus R2. Again, these are what happened? These are This is a base displacement addressing mode. The base register is R2. The offset 2345 is added to it to calculate the address of the memory which has to be accessed. So after that memory is accessed, I'll just draw it for you again. So maybe, so this location corresponds to R2 plus 2345, right? Now, when we are accessing this memory, the data from here is picked up and placed into register R1. So this is a register R1, right? Now, in R1, the numbering of bits is like this. So we have 31 here, and we have the 0th bit here, right? Now what happens? When the operation says load half word, it picks up 16 bits. This means data from two consecutive memory locations, right? Places it into the register, and the higher order bits which were left unused earlier, which were filled with the sign bit of the data. Excuse me, just a minute. Yes. So, which were, earlier filled with the sign bit of the data, are now filled with zeros. I hope you're getting what I'm trying to say.
Yes, ma'am.
ये मैंने बताया था लास्ट टाइम आपको कि वो साइन बिट होता है उसमें.
Yes,
Yes,
ma'am.
ma'am, आपने ये बताया था.
हाँ, good. So if I've told, we just have to correlate now. So if I'm loading a half word, this half word occupies from 0 to the 16th bit. So 0 to 15 will be the number of bit positions which will be occupied with the data. The higher order bit positions which are unoccupied in the register are now filled with 0 because it is an unsigned load operation. Would have I given a load half word operation, this would have filled the unused bits of the register with a sign bit of the data. तो यहाँ शायद 1 या 0 जो भी उसका sign bit होगा वो आ जाएगा. Anyone who will tell me what is a sign bit?
Ma'am, sign bit tells us whether the number is positive or negative.
Okay. What is the range of signed numbers that we have if for a 32-bit number?
That I don't
2 power
remember.
31.
Very good. 2 to the power 31 plus minus. So if I am saying that I have if I have a 32-bit number, I'll just draw it again for you. So if I have a 32-bit number wherein I have a 0 here and the 32th bit is here, right? This last bit is referred to as the sign bit. This will not correspond to the data values, right? So you will have 0 to 30 as the total number of bits identifying the data. Now what happens? You will have the range as 2 raised to the power 31 plus and 2 raised to the power 31 in the minus range. So from plus 2 raised to the power 31 to minus 2 raised to the power 31 will be the range of data that combinations that this number can occupy. I hope it's clear to everyone. Clear hai?
Yes, ma'am.
Okay, so moving on. Yes. The next set of operations that we'll be discussing today are the ALU operations. Again, as the name signifies, we have the arithmetical and logical operations being carried out under this category, right? So when we talk about arithmetic, we have the add, subtract, multiply, divide, all falling under this category. And when we talk about logical, we have the and, or, we have XOR, we have shift, we have compare, um, set greater than, set less than. So all arithmetic and logical operations together under one category. Let us start with the arithmetic operations first. The first operation is add and the next one is subtract. So if you can just see here, yes. So if you can just see here, this is add r1 comma r2 comma r3. I guess this is the most simplest operation that we have been discussing till now. So every time I take an example in the class, I take the example of add only. So what should this do?
Ma'am, it will take the contents of R3 and the contents of R2, add or subtract them, and then place the result in R1.
Yes, very right. And this is a signed addition, please remember. So we have to take into consideration that this is a signed addition that is taking place. If I suffix a u outside the add, that time it becomes an unsigned operation, right? So starting with the first one, this is an add operation. This is add r1 comma r2 comma r3. This will add the contents of r2 and r3 and store the result in register r1. The operation will be a signed operation. This is what type of addressing mode? This is what type of addressing mode?
Register addressing mode.
Very good. Very good. This is a register addressing mode and an R type of encoding that we follow here. So I'm not going to write now. All right. The next operation again in the same category is the add unsigned and the subtract unsigned. So I guess subtract will follow the same. It will subtract R2 and R3 and store the result into register R1. Again, signed subtraction, right? So when we move on to the unsigned, the all other things remain the same, just that the numbers are not treated as signed numbers now. So if I give an operation of add unsigned, it will treat the contents of R2 and R3 as unsigned numbers and store the result after performing addition into register R1. A subtract unsigned again will subtract R2 and R3 and store the result to R1. Again, the subtraction will be an unsigned operation. Again, R type instructions and a register addressing mode. Now, these add and subtract operations do have an immediate format as well. So if I give an operation of the kind add immediate R1 comma R2 hash 32 23h, and then I give one more operation add unsigned immediate, again let's take it the same r1 comma r2 hash 23h. Yes, so what will this operation do, Aryan? Aryan, please speak up. Yes, what will this operation do? ओ भाई इतना टाइम नहीं है. Okay, so again the operation is the same. It is an add or add unsigned operation as discussed earlier, just that the type of addressing mode is different. The type of encoding format is different now. So I have used an immediate addressing mode here. Whatever data was there that has to be added to the contents of R2 is now specified using a immediate value into the instruction. So I have 23, which is added to the contents of R2 signed addition and the result stored in the register R1. Now if I give the operation as unsigned, so add unsigned immediate R1 comma R2. So R2 and R23 will be added as unsigned numbers now. The contents of R2 will be added to 23 as an unsigned addition and the result gets stored to register R1. Similar follows with subtract immediate and subtract unsigned immediate. Clear? Please speak up if it's not clear.
मैम ये वैल्यू ओवरराइट होती रहेगी कि पहले ऐड का स्टोर होगा उसके बाद फिर सब्ट्रैक्ट का स्टोर होगा आंसर?
वो डिपेंड करता है कि हमने कोड कैसे लिखा है। अगर हम कोड ऐसे लिखेंगे तो ओवरराइट हो जाएगी, बट ये आपको सिर्फ एग्जांपल देने के लिए सेम फॉर्मेट के साथ मैंने एक्सप्लेन किया है। Let me tell you, okay, if you can't understand. Say suppose I had, written a code like this. I had load word into R1, say from 234 R2. Then say I have load word into R3 from 238, say R2, and then I add R2, R3, R4. So I add R4 with I add R1 and R3 and I store the result in R4. ठीक है, अब अगर मैं subtract कर देती हूँ, if now I perform subtract, so I perform R1 comma R4, sorry, this is R4, 3, R4 comma R1 comma R3. अब ये तो कोड ही हमने ऐसे लिख दिया कि हमने दो वर्ड्स लोड किए रजिस्टर R1 में और R3 में कंसेक्यूटिव मेमोरी लोकेशन से, ठीक है। उसके बाद वी हैव एडेड द 2 एंड स्टोर्ड द रिजल्ट टू R4. Then we have subtracted the 2 and stored the result to R4. Now in this case your R4 will get overwritten. Well, what I was telling you earlier were just two examples with the same syntax and everything same. So it is the way you write the code. You are the owner. Are you getting?
Yes ma'am.
All right. So I'll just move on. यहाँ तक clear है सबको?
Yes sir.
Yes, ma'am.
Okay. Oh, just a minute. I'll open the next set of slides. Okay, so the next set of ALU operations are the, see, multiply and divide I will teach you in the end, because when we talk about multiply and divide operations, they cannot be performed on GPRs. We need to use floating point registers for multiply and divide, and before that you need to study move operations. So till now we have not discussed move operations. So multiply and divide we will be discussing after we discuss the move operations. All right. So the next set of arithmetic and logical operations are actually the shift operations. So this comes under the category of logical operations, right? Now, as the name signifies, they shift the contents of the register by the amount specified in the instruction. And the maximum shift that is possible in one go is just 5 bits at a time. The operations are shift logical left. I'll take a marker. Yes, so the operations are shift logical left, shift right logical, shift right arithmetic, and then in the immediate mode also we have. Let me take one by one. Now suppose I have to give an operation of shift left logical, the contents of register R2 by amount specified in register R3. First of all, this amount which I am mentioning in register R3 cannot be greater than 5. All right, so this is the the hardware specification. We cannot in one go, we cannot shift the contents of any register by more than 5 bits. तो 5 bits का shift एक time पे possible है, right? Then so when we give this command SLL R1 R2 R3, this will shift the contents of source register R2 by an amount specified in the register R3. In any case, R3 cannot be greater than 5. So that we have to, as a programmer, we have to make sure, otherwise this runs into a syntax error. All right. Then shift logical left, as the name signifies, will shift the data towards left. See, it is always towards. The point is that we have to take care of the term towards. It is when it says left shift, the shift is towards left. When it is right shift, the shift is towards right. Right? So shift logical left the contents of R2 by an amount specified in register R3 and store the result into register R1. All right. Now let us see the diagram which is here. Yes. So suppose we have register R2 as 32 bits. So 0 starting here and 31 bit or the 32 bit which is from 0 to 31 is here, right? I give a command shift logical left R1 comma R2 comma R3. So suppose R3 is 3 right now. So what happens? The contents of R2 start getting shifted towards left. So the MSB position goes vanished. This came here, vanished. Then the next one vanished. So what happens? We have 3-bit positions left vacant here. Are you getting, everyone? Should I repeat?
Yes, ma'am.
यस मैम रिपीट कर दो.
अच्छा हम एग्जांपल ले लेते हैं फिर ठहर जाओ. 1 2 3 4 5. Okay, suppose these are this is the data which is available in register R2, right? And R3 has a value which is say 3 right now. So what happens? I give a command shift logical left R1 comma R2 comma R3. This means I have to shift the contents which is this. Something is wrong today. I don't know. इसका font बड़ा हो गया. I'm putting it here. Yes. So, are you able to see? चलो अब ठीक है ना. I think we can do it now. So if we just see the data, say this is the contents of register R2 and we want to shift it by 3-bit positions towards left. So we give a command shift logical left R1 comma R2 comma R3. Now R3 has a value of 3 suppose. So what happens? This data has to start shifting towards left, right? So towards left means from the MSB. So 1 bit gone, next bit gone, third bit gone. यहाँ पर 3 vacant spaces create हो जाएंगी. Are you getting?
Yes, ma'am.
Yes. So these 3 vacant spaces will be occupied with 3 zeros. That's it. So whatever the new data is formed is by shifting the available data by the number of bit positions specified in the register R3, and then how many spaces that are created vacant in the data are now occupied with zeros. I just hope it's clear now. I hope it's clear.
मैम तो यहाँ पे हमने 3 रजिस्टर्स क्यों यूज करे?
अच्छा हाँ, तीसरा रजिस्टर आपका डेस्टिनेशन रजिस्टर है. जैसे अब मैंने कमांड दी SLL R1 R2 R3. R2 में मेरा डेटा था सोर्स रजिस्टर 1. दिस इज एन R टाइप एनकोडिंग है ना. In the R-type encoding, just remember what all did we have? What all did we have? We had the opcode, then we had the source register 1, then we had the source register 2, then we had the destination register, and then we had the function bits, right? ऐसे था?
Yes, ma'am.
11 बिट्स का फंक्शन था, 6 बिट्स का ऑपकोड था और 5 बिट्स के तीनों रजिस्टर थे, ऐसे ही था, ठीक है? सो योर SLL is encoded using opcode plus function bits, right? Source register 1 is your actual data that you want to shift, so that is R2 here, encoded here. Source register 2, the number of bit positions you want your data to shift, so R3 encoded here. And where would you place the data after it is modified? You want to place it in R1. So the destination register is R1. So जो new data आपने create किया है by shifting the available data of R2 by 3 bit positions and occupying the unused bit positions by zeros is now placed, the modified data is now placed in register R1. I hope it's clear now.
Yes, ma'am.
Okay, good. So yes, so this was shift logical left. We do have instructions of shift right logical as well. So suppose I again give the same command, a command of the same type. I have I think I've written here. Okay, let me write again. So this is the shift right logical, the contents of R2 by an amount specified in register R3 and store the result after shifting into the destination register R1, right? Now, the operation says shift the contents of the register R2 towards right. This means I should start shifting from LSB or MSB now.
LSB.
Very good. So in the big endian mode, we have LSB on the right and MSB on the left. Accordingly, we start shifting from the right now, okay, towards the right. So we have data here. Say suppose R3 had to be R3 is equal to 2 now. Say it's equal to 2. And we have to shift the data by 2 bit positions. So we give this command, we store R3 equal to 2 and then we shift right logical R2 by 2 bit positions and store the result in R1. Everything else is same, just that now you will have vacant spaces created here. यहाँ पे 2 spaces vacant हो जाएंगी. एक बिट पोजीशन गई, वैनिश हो गई, दूसरी बिट पोजीशन गई, वैनिश हो गई, तो यहाँ पर 2 बिट पोजीशंस खाली हो जाएंगी और वहां पर हम प्लेस करेंगे 2 zeros and the final data that would be formed will be placed in register R1. ये क्लियर है सबको?
Yes, ma'am.
एक दो तीन चार पाँच छः सात. Okay, now who would tell me what will be the new data which will be formed after performing this operation? Say suppose we have this data as 1 0 0 0 0 1, all ones, then all ones, then all ones, and this is the 32-bit data that is available to me in register R2. Now I place R3 with a new value which is 2 and I give a command shift right logical R1, R2, R3. What should happen? How will the data get modified?
Ma'am, the LSB bits of last two LSB bits will be vanished and whole data will be shifted towards right with 2 and the first two MSB bits will be 0.
Very good. Absolutely correct. And I have drawn the results on the screen as well. So we have 2 bit positions shifted towards right and on the left we have 2 bit positions which are vacated. Accordingly, 2 zeros are inserted on the 2 left side positions and the new data can be formed accordingly. Now we have to start, encoding like this. So so 4 bits again encoded, and the new data can be formed accordingly. I hope it's clear to everyone now. Okay?
Yes,
Yes,
ma'am.
ma'am.
Good. Now, we do have commands like shift left logical immediate and shift right logical immediate. Everything else remains same, just that now we have an immediate addressing mode and an I-type encoding. So I'll just write down an example here. So if I give a command shift left logical immediate R1 comma R2 hash say 5. Now, whatever I want, the number of bit positions that I want the data of R2 to shift, I have mentioned the value directly in the instruction. Here also it cannot exceed 5 in one go. This is the restriction on the hardware that we have. तो 5 बिट से ज़्यादा in one go हम ही shift कर सकते हैं, ठीक है. बाकी ऑपरेशन वही है, सिर्फ ये आई टाइप एनकोडिंग फॉलो करेगा. और कौन सा एड्रेसिंग मोड है?
Immediate.
Very good. So this is an immediate addressing mode. This is only a way of specifying the operand has changed. Rest the operation remains the same. Similarly, for right logical immediate also, we can give a command like shift right logical immediate R1 comma R2 say hash 3. So same operation, just that it is an I-type encoding and an immediate addressing mode. Rest everything remains the same. Okay, I hope everything is clear till here to everyone.
Yes, ma'am.
Okay, the next operation that we have is shift right arithmetic and shift right arithmetic immediate. So SRA R1 comma R2 comma R3, or we have shift right arithmetic immediate R1 comma R2 hash 3. So now shift right arithmetic will perform the same operation, just that now the number of bit positions that the data has shifted towards right, the MSB positions which are vacated will be occupied with the ones, not the data. Or I can say not one also, it is the sign bit of the data which is occupied in the
previous MSB will be retained.
Come again, Ankit, what are you saying?
The previous MSB will be retained whether it's 1 or 0.
No, it will not be the previous MSB. It will be the new MSB after your data has shifted. So if suppose I give a command shift right arithmetic R1 comma R2 comma R3, and suppose R2 had say F102 and say 3214 in hexadecimal, the 32-bit data like this, right? So F is right now 1111, all ones. So even after shifting 2-bit positions towards right, it will have the MSB as 1. So that 1 will be replicated here in the 2 unused bit positions. For the new data, it will not be 0 now. If I had say this as 1102, समझ आ रहा है?
Yes, ma'am.
So suppose this was 1102, this means it will 0001. So 0001, and if I've shifted it by 2-bit positions towards right, this means 2 वहां से गया तो यहाँ पे 0 रहा. Now it will be the 0 which will be replicated here. So shift right arithmetic actually replicates the sign bit of the new data which is there, right? तो जो भी आपका न्यू डेटा बनेगा उसका साइन बिट यहाँ पे रेप्लिकेट हो जाएगा. जो चला गया वो लॉस्ट है भाई, उसकी चिंता हमने नहीं करनी. और वैसे भी हम राइट शिफ्ट कर रहे हैं तो डेटा इस साइड से जा रहा है, वहां से तो जा ही नहीं रहा. Are you getting, Ankit?
Yes, ma'am.
हाँ, तो साइन बिट ऑफ द डेटा गेट्स रेप्लिकेटेड, ठीक है. And shift right arithmetic immediate is again the same, just that now we are following a immediate addressing mode. ये clear है सबको?
Yes, ma'am.
Yes, ma'am.
Very good. So I'll just move on. Yes. I'll move on to the next slide. All right. The next operation is the logical operations. We have started with the arithmetic and logical operations. So the next logical group is the AND or XOR, and we have load high immediate. So starting with the first one, the AND operation. So again, I can give a command like this, and R1, R3, R4, suppose. So this will bit by bit and the contents, logically and the contents of R3 and R4 and store the result in register R1. When I say bit by bit and, what does it mean?
मैम इट मीन्स कि जो भी रिस्पेक्टिव बिट्स होंगी डिफरेंट दोनों रजिस्टर की कंटेंट्स की दे विल बी मतलब उनका एंड होगा एंड देन द रिजल्ट विल बी स्टोर्ड इन आर like the 31st bit of the content of R3 will be ANDed with the 31st bit of the content of R4.
Very good, बिल्कुल ठीक बताया है. हम बिल्कुल बिट बाय बिट ऐसे ही एंड करेंगे. बिट पोजीशंस रिस्पेक्टिव होंगी. So 0th bit with the 0th bit, first bit with the first bit, 31st bit with the 31st bit, and so on. So this has to be bit by bit ANDing of the data. And secondly, when we AND, we follow the same truth table as we were following in second year of our digital electronics. So the rules remain the same. 1 ANDed with 1 gives
1.
1 ANDed with 0 gives
0.
Very good. So it has to be, the rules remain, the truth table remains the same, right? Now, similar holds for OR. So I can give a command. Similar holds for OR for XOR as well. So if I say OR R1, R5, R6, this will logically bit by bit OR the contents of R5 and R6 and store the results to the register R1. Again, the truth table for the OR operation remains the same. We cannot change it, right? And similar follows for XOR as well. So your XOR operation will bit by bit XOR the contents of R5 and R6 and store the result to R1. Then we have, this is what addressing mode? This is what addressing mode?
Immediate addressing.
Register addressing and R-type encoding. Very simple. We can just see and analyze, right? Again, we have an option of immediate addressing here as well. We have AND immediate, XOR immediate, or we have the OR immediate. I don't think I need to explain this in detail. ये अब आपको आ गया होगा अब तक. अब अगर मैं एक ऑपरेशन देती हूँ XOR immediate, XORI, say R1, R7, hash 45, 345, suppose. What should happen? What should happen?
मैम R7 और जो वैल्यू गिवन है उन दोनों का XOR होके रिजल्ट R1 में स्टोर हो जाएगा.
बिल्कुल बिल्कुल, absolutely right. But please remember that R7 has a 32-bit value and this data is how much?
16-bit.
Very good. This cannot be greater than 16-bit in an immediate addressing mode because the maximum I-type encoding format can support a 16-bit. 6 bits का opcode, 5 bits का destination register, 5 bits का source register और 16 bits का immediate data. ठीक है? तो अब अगर हमारा जब बिट बाय बिट और हो रहा है या एक्सॉर हो रहा है या एंड हो रहा है तो ये लोअर ऑर्डर बिट्स के साथ होगा. You just have to remember this, that this is with the lower order bits of the data which is there in R7. I hope that's clear. Higher order
Yes,
bits will be zeros, will be treated as zeros. Okay, moving on. This is the load high immediate instruction. This is a very important instruction for you all in terms of programming. So whenever you do the programming, there is there is no direct instruction with which you can load any register with a 32-bit value. Why? Why can't you do that? Because every instruction has a length of 32 bits. 6 bits at the most have to be occupied by the opcode. And if you have to load a register, 5 bits for the register as well, makes 11 bits. है ना?
Yes, ma'am.
So if 11 bits out of 32 are gone, I am left with just 21. I have no option. I don't have an alternative. There is no provision that I can load any register with a 32-bit value immediately. I cannot do that. So in order to form, sometimes form a 32-bit value into a register, we follow this instruction. This is load high immediate. As the name signifies, this will load the higher order bit positions of the specified register by the value specified in the instruction. So suppose I give an instruction of load high immediate R1, #1234H. Now this is a 16-bit value, but the operation says load high immediate. So this loads this 16-bit value into the higher order bit positions of the register. So from 16 to 31-bit positions are occupied with 1, 2, 3, 4H and the lower order bit positions are all filled with zeros. ठीक है. अब अगर मुझे एक वैल्यू बनानी थी एक रजिस्टर में, से आई हैव टू फॉर्म अ वैल्यू इन R1 इक्वल टू 1 2 3 4 FF00H. आ रहा है, समझ आ रहा है सबको?
Yes, ma'am.
Okay, so I can always give a command like load high immediate into R1 from 1 2 3 4 34H. हो गया? This makes the higher order bit positions of R1 to be loaded with 1 2 3 4, and then the lower order bit positions are all filled with 0. Now if I give a command of add immediate R1 R1 FF00 00H, बताइए what will be the result in R1?
Ma'am, it will be the previous value.
Same. Previous.
Same जो पहले था R1.
हाँ, हमें वो बनाना है, previous value नहीं है, वो हमें बनाना है. That's what I'm saying.
Okay.
I want to load R1 with a value which is 1 2 3 4 FF00H. So in order to achieve that, I have no instruction which can directly load a 32-bit value into R1. Well, I can do this using two steps. I can load the higher order bit positions of R1 with a value, and then when I add immediate, automatically the 16-bit value which is specified in the instruction is added on the lower bit positions. तो यहाँ पे था, यहाँ पे आपका आ गया, let me write down. So you have 1 2 3 4 loaded here, right? And you have 0 0 0 0 loaded here after this operation is performed, this one. So after this is performed, right? Load high immediate into R1 1 2 3 4H. अब अगर मैं add immediate करती हूँ FF00H, तो क्या होता है कि because I am giving a 16-bit value in the instruction, by default this is going to add FF00 to the lower bit positions, and what resultant I will get will be 1 2 3 4 FF00. I hope it's clear now. ये इंस्ट्रक्शन ये ऑलमोस्ट हर कोड में आपको एड्रेस ऐसे ही फॉर्म करना पड़ेगा, because there's no other option available. Okay, I guess time हो गया है, it's 10:31. So we are left with, I guess, just one or two set of instructions, and then we'll start with the coding of this processor. Till here, I hope it's clear to everyone.